you don't need this metal rod. This was available only once worldwide, and nowadays light is available everywhere. Yeah? But you need the light in vacuum. That means it's not traveling through air, it's traveling in vacuum. But it's not a problem, you can evacuate some tube and then try it there. But what does this mean? That means that we do not have a standard for the meter itself, because we got a standard for the second. We got the number for the speed of light, and out of this we can calculate the meter. So that's how the meter is defined. The meter is the distance that light will travel within 1 over 299,748 of a second. That's how the meter is defined. It's defined as the distance that light will travel in this amount of time. So we will need a second. Any questions? Except if you do have to know that number. Okay, so then we got the meter. The next one is the mass. It's not the weight. Huh? It's mass. Because weight depends on where you are. With mass we still got a problem, because there is no idea how to refer it to some physical quality, like the cesium atoms. But in the last year there was some ideas to reference it to a certain number of silicon atoms. Why silicon? Because silicon is known from the electronic industry. It's the basic of every chip. For the semiconductors. Yeah? So the idea is to produce a silicon sphere with a certain number of silicon atoms, and this certain number of silicon atoms will give you exactly the mass of 1 kilogram. So, and how do we know how many atoms are there?
4.
4?
No, in the last layer of...
Yeah, in the last layer of the silicon atoms. Yeah. But for 1 kilogram, we will need a lot more than 4 atoms. But the crystal lattice is this tetrahedral structure. So we can calculate the volume of this amount of silicon that will sum up to 1 kilogram. So all we have to do is to measure the diameter of this sphere, and then we know we know roughly the number of atoms.
Well, because it's impossible to know exactly. Huh?
Yeah. Under the condition that the lattice structure is perfect. And that's why we use silicon, because with silicon we nearly can produce a perfect lattice over some region.
But there is, but it's impossible also to know exactly silicon. It's not that accurate because there is no such surface is flat.
Yeah.
It should be there is hole. There
That's
is.
the problem. But they are working on that sphere for more than a year now, so it's pretty flat.
Okay.
But you are quite right. But it doesn't depend on 1 or 2 atoms. So, because the nowadays standard of 1 kilogram is pretty a mess. It's a platinum iridium cylinder. This is not a cylinder, this is maybe a cube. But think of that. And that has the mass of 1 kilogram. So that's the same problem like with the meter. There is only one prototype of that. So with the meter prototype, it's only one prototype for mass. It's in Sèvres near Paris. And in Vienna we don't know how to access this. So that's the same problem. That's the idea of this sphere, because you can produce a lot of these spheres, and every lab got his own sphere, because the material is not very expensive, silicon. It's a pure sand. You find it at the beach. And the only thing that is really hard to get is the ideal sphere. But it takes a lot of time to produce that. But the costly thing is the manufacturing process, not the material itself. So but these are only ideas. Until nowadays, the mass is defined via this 1 kilogram prototype in Paris. So there's no other ideas.
So to define the kilogram, we need kilogram.
Yeah. It was, on a historical scale, it emerges out of 1 liter of water. But the problem with water is that it's a little polluted, or salt water, or sweet water. So if you use salt water, then it's got a different mass. So that's the problem with water. And this prototype was manufactured in a way so that it comes very close to 1 liter of water. And this is what we got nowadays. So it's a matter of definition, the same with frequency. This number is defined, or the speed of light is also defined. But before we had a good idea of how fast is light. And since we had the idea, we can define a close number to the speed of light. And this will alter the meter, but to a minute amount. So that's not a problem. And here we got the same. We got the 1 liter of water. We manufactured a prototype of platinum iridium. This is a very stable combination. Yeah? It's a stable alloy. It's platinum and iridium. So if you do the same with iron, you got the problem of oxidation, and it will get lighter and lighter all the time. But with platinum iridium, it's stable. So that's how we have the 1 kilogram prototype. But there's only one available worldwide. So if you want to do an exact measurement in relation to this prototype, you have to travel to Paris.
Why they don't, make some prototype of
They
these
do,
things?
yeah.
They do?
They do produce some second level prototypes. You got in every national normation institute, you got a second level prototype. But there you have to travel every 1 or 2 years to Paris and to compare it with the original, to do a recalibration.
Good idea.
But it's a nice job, no?
Yeah, to trip.
Travel to Paris, do a measurement, and
One day.
once a year. The rest of the year you're free. So we got the mass. What else do we have? Temperature. Huh? Mass.
Kilogram.
Temperature, what's the unit of temperature?
Celsius or Kelvin, okay.
Kelvin.
Celsius and
Named after a British physicist, also Lord Kelvin. And the funny thing about the Kelvin is if you're measuring temperature differences, it's the same number compared with Celsius. So this, obviously you know the story, this is the next step following the Celsius scale. How is the Celsius scale defined? Well, what is the idea? This is dating from the French Revolution. What is the idea of the Celsius scale?
It's a triple
At
point.
temperature which the water will be ice. Will
Ice?
freeze.
Yeah,
And then boil.
and water. Exactly. The Celsius is between the freezing point of water and the boiling point. So this is 0. This was 100 degrees Celsius.
Under the
So you
pressure
see
of-
also the idea of the French Revolution. There are the decimal system. If you compare this to a British numbers, they always got some very strange numbers, 1/16 or. But here the French physicists, they had decimal numbers 0 and 100, and they divided this temperature range in 100 steps, and 1 steps is 1 degree Celsius. But since this the ice point and the boiling point of water, is this all the time the same?
No.
It depends on the temperature.
It depends on the atmospheric pressure. And this is the critical point on this definition. So this, the Kelvin is a little bit of an improvement. Here we use the triple point. I guess only 1p triple point. So what will the triple point be?
The point where it is neither ice nor water or gas. It's
So nothing of
all
that.
three
All three, yeah.
in 1 point.
Exactly. This is the triple point. We stay with water. And the triple point is the point where you can find water in a solid, liquid and gaseous condition. But this is not available under normal atmospheric pressure. Now you have to lower the pressure, and then you can find this triple point. Here you got the exact scale in the script, but it's something around here. This is 237.16. You see the numbers? To be compatible with the Celsius scale, and it's roughly around 611 Pascal as a pressure. So this is way below atmospheric pressure, because atmospheric pressure is around 100,000 pascals, and this is around 611. So if you increase the pressure, then you have only solid, liquid and gaseous, and no solid phase. That's why we have to lower the pressure, and we have also our solid phase. So, and that's the definition of the Kelvin.
Gas.
The Kelvin is a fraction of the thermodynamic triple point of water, and this fraction is 1/273.16.
Can you say again the definition of the
Okay. The definition of the Kelvin is defined as a fraction of the thermodynamic temperature of the triple point of water. But you guide in the script. Because these are always definitions, and the wording is pretty hard.
At that point, the modes of water is like gas and also
Gas,
liquid.
liquid, and solid.
All the three
All the three
in this one.
in this point.
How?
That's the problem, that you have to lower the atmospheric pressure. Because under normal atmospheric pressure you got solid or liquid,
Or gas.
or gas and liquid. This is the Celsius scale. But if you lower the pressure, then there are all three there. This you have to believe.
How does it look like?
Because no one can reach
I doesn't have
Have
seen
we
it.
done before?
Sorry?
Have we done the experiment before?
This will be pretty hard in the lab.
Yeah,
Because
maybe.
you have to have very pure water, and then you have to have a chamber and reduce the pressure. Reducing the pressure is not that problem, because there are air pumps that can easily reach that level, because it's not very low. In physics you can have pressure of
But
10 to the minus 9th atmospheres.
Yeah, but you start with the solid condition, right?
You start with solid water.
Yeah.
Solid and gaseous is here anyway. And then you reduce the pressure to this number, and then you reduce the temperature. And at that point, when the liquid gets to solid, this is the thermodynamical temperature of the triple point of water.
But did anyone try it before?
Yeah, for sure.
Okay.
It's
Because
good. It works.
maybe it's just only Kelvin did it.
No. No, Kelvin did it not.
Okay.
Because at that time it was around 1790. But it was named in honor of him.
Uh-huh.
He had the idea of a unified temperature scale. So why do we need a Kelvin scale? And this is a pretty curious number. That means that 0 degrees Celsius corresponds to 233.16 Kelvin. But the idea at that time was, what is temperature? And can we arbitrarily reduce temperature? But you cannot. There is one point at that you cannot reduce temperature anymore, because there's a final point there. So what is temperature at all?
Potential energy of atoms. Movements of atoms.
Movement, but it's not potential energy. This is kinetic energy.
Kinetic energy.
So that means that temperature is pretty different to, let's say, a meter. Meter is, but temperature, this is only a statistical quality, because it's a movement of a huge number of atoms. And if all the atoms come to a standstill, then we got 0 Kelvin. So that's the point where all the movement stops. This no one has seen before. Currently we are at 1 a fraction of 1/6 millionth of a Kelvin. There's a very, very slow movement. This you can see with atomic force microscopy. But this costed also nearly $6 million to reach this point. But that's
Why do we want to reach this point, the 0
a
Kelvin?
good question. There's a lot of money we put in anyway. But at that temperature, the quantum physics, you can monitor quantum physics. Because then the movement is so slow that there are some specific arrangement of the atoms in relation to each other, and then you can study quantum physics.
Wouldn't the object with 0 Kelvin invisible because there's no radiation of photons anymore?
Might be. But the problem is that these objects will be invisible anyway, because they have to be in some,
Yeah, it wouldn't be
also
detected
in a cavity. Because you cannot put that object right here on the table, because of all the thermal energy from the environment, it would heat up immediately. So, but I think, I don't know if it's invisible. It absorbs every kind of energy, yeah? But if you put it in front of a white wall, then it would be black.
Yeah, it wouldn't be detectable in any range
Yeah.
of the spectrum.
Yeah. But you can detect the absence of every kind of radiation. Because if you compare it with the background, then there is just a black thing. But this is a philosophical question. So then we got the temperature. So maybe it's invisible at 0 Kelvin. So what else do we have? We got 4, so there are 3 missing.
Pressure.
Pressure,
No.
no.
Okay. We have 4 now.
4.
Yeah. There's 2 missing.
3 missing. Yeah.
3 missing. Yeah.
We got
7. Yeah, 7 stuff.
So 4. So what is missing?
Energy. Calorie.
No, energy is also not.
Moment.
What also not?
Light.
Light. Yeah.
Mm.
The intensity of light.
Maybe sound also.
Sound? No. But if you're thinking about electronics, so there is no electronic unity here. The current we have, yeah.
Yeah.
Why do we have current? Wouldn't voltage be nicer?
Yeah, because the voltage is defined by current.
But nowadays, if you're looking for instruments, it's much more easier to measure voltage than current.
Yeah.
But nevertheless, we got a unit for current and no base unit for voltage.
Because you said before that the current, we measure it with electrons.
This is also, you have to go back maybe 100 years.
Mhm.
And how did you measure electricity back then? There were no measurement on voltage. This is a pretty new
Yeah.
development. Because the electronic instrument measures voltage. But if you're thinking about the electromechanical instrument, this will measure current. And how did the instruments measure current? How can we, on a physical scale, detect if there is current flowing somewhere? Is there any clue on that? For voltage, it's pretty hard. Because the only clue to voltage, since voltage is a potential difference, is an electric field. Now, if you've got one object with some charge and another object with a negative charge, maybe a proton and an electron, there is an electric field. That's the only clue. And the electric field will give you the potential difference, the voltage. But current flow, how can we detect current flow? Any idea?
By number of
Electrons.
Magnetism.
Number of electrons per second, that's the definition, but
Yeah,
no one ever has seen an electron.
Yeah, that's.
But it works pretty well, the idea. But no one has ever seen one. And no one has ever measured one single electron. So you cannot count the electrons in the wire.
Of course.
No way.
The movement, as you said, in a wire, the movement of one electron, which move the set of electrons in a wire. So, it's not idealistic that one electron release from another part of the wire.
You think you're in the lab, and how will you detect if there is a current in a wire or not?
The effect of the current.
What is the effect of current?
For example, if we put a lamp to light.
A magnetic field.
A magnetic field, that's the only clue, yeah? Because you can touch the wire,
Yeah.
it doesn't harm you if there's current flowing. The voltage will harm you, but the current in the wire, no problem. If there is a current maybe of 1000 amps through a copper wire and you touch the wire, this won't harm you. But what they did, they used a compass needle, and if you turn on
Okay, there is a
the
magnetic
current,
field.
there is a deflection of this compass needle. Our instruments nowadays are a little bit better than this, but this was the first clue that there is something going on there. No one knew what was going on there. So that was Rutherford, was the first that developed the idea of an electron. And before, they only had the idea there is something in there, and they only knew that they had to connect it in some certain way, so that, and if you cut it on one position, that this
current
will stop. And so this was the idea, like in a pipe system, that there is flowing there something. But no one knew what was flowing there. Huh? So the idea for current is the current will produce a magnetic field. There is also an equation for that. The magnetic field equals current over 2πr. Now we'll need a little sketch to understand that. So let's suppose we got a wire and the current is flowing in that direction. You're familiar with that sign?
Yeah.
No. Everyone? Who's not? That's everyone. Okay, so the current is flowing in that direction. And then we can draw the field lines for the magnetic field. Because the magnetic field is a curl around that conductor. So the magnetic field lines are concentric circles with the conductor in the center, and the direction you can estimate with, take the right hand. The thumb is directing in the direction of current flow, and bend it that way, the other way it's pretty hard. Then, and the magnetic field vectors will go into that direction. And the size of the amount of magnetic field is given by that equation. Huh? That means the farther you are away from the wire, the field is dropping. If you're getting this in a graph, then it will look like that. This is the radius, this is the field. So the first question, what is with radius 0? Then the field will be infinite. But that's obviously a problem. But the equation is only valid for r bigger than the radius of the wire.
Of course.
It's only valid for the outside of the wire, this equation. Inside of the wire, so we got r here, then there is a linear drop in magnetic field strength. Huh?
Because it starts from 0. From the
To
origin.
avoid this 0
Yeah?
pole. Because within the wire, the amount of electrons you are taking, you are accounting for is smaller and smaller. So within the wire, the magnetic field strength drops linearly. On the outside, it's 1 over r.
There's 2 pi r, I,
2 pi r.
2 pi r.
And that's how we can define the amp of current strength. The unit is amp. And the definition is pretty curious. But as you can see from here, it must be linked to the magnetic field. The idea is you are in a vacuum chamber, a very big chamber, because you have to use infinite length of the wires. So the length is infinite. The distance is exactly 1 meter. So then every wire will produce its own magnetic field surrounding the wire. And somewhere in the middle, the two fields will overlap. And if two fields will overlap, what is the result of that? It's the two magnetic fields overlap.
You have to see the
I think the compass will not move.
If they compensate, then it will not move. Yeah? But two fields always acting on each other, and the result is a force, an acting force.
Yeah.
So it's the gravitational field of two planets or two electric fields. If they are acting on each other, then it's always a force. And if a current of 1 amp is flowing in both of the conductors, then the force is 2 times 10 raised to the power of -7 Newton. So you see, this cannot be ever handled in a realistic lab situation, because the length of the conductors is infinite. You cannot set up this in a lab. But that's the definition. And that's all.
Or the H is instead of E because we showed it.
This is the same like we had before.
E.
1I over
H
2 pi.
2 by R.
We used to use the B instead of H. H is German.
P is resistance. P is
B is P for
Magnetic flux.
Phi.
No.
Yes, sir.
B and H.
B. We used B. B. No, B.
P.
A, B.
P for pen.
B.
B. B is the magnetic flux density. B is equal to
Rho.
mu times H.
So it's different.
That's different. B is the magnetic flux density, and H is the magnetic field strength. So when we just say magnetic field, it's always H. Because B is the flux density. The flux density, you can think of the density of the field lines. The more field lines per square meter, the higher the flux density. Okay, then we got current. Then we got the light and the mole. It's the seventh one. But this we'll handle them that much. So what's the time? 1. It's 1.
Yeah, 1 o'clock.
We got half an hour we got left, huh?
20 minutes without break.
Okay, 20 minutes then. Okay, since the next time we will go to the lab, you can read the definitions for the light strength and the mole at the script. for the remaining 20 minutes, we will do a little preparation for the lab, because next time we will go to the lab and to have this exercise from the last lecture. So I will recall this and give you some information on what you have to set up in the lab. Because I would not like to do that in the lab, because it's not worth the time. When we are not that often in the lab, so when you are in the lab, you should be working with the instruments. So, we will start. There you also can think about frequency and how to measure frequency. Yeah? So that's very good, because we will produce a sinusoidal waveform. With our generator. So this might be the output of our acoustic sensors from the last session. Normally, if you're monitoring the noise on the street, it's not exactly a sinusoidal wave, but the idea is that sinusoidal. So this is the output of our microphone. And then we have said the last time that we will need an amplifier to amplify this signal. But for now, since we are producing that signal with a generator, you can set any amplitude you would like. So the amplitude is the size of the signal. So on the generator, we set a frequency of 1000 Hertz, and we set an amplitude of, let's say, 10 volts. Peak to peak. That means that from the positive peak to the negative peak, the difference is exactly 10 volt peak to peak. 10 volt is 10 volt, but normally we state that is from peak to peak, because maybe it also can be only one half. So if we state peak to peak, then we know that's from the positive maximum to the negative maximum. And then we do a rectification. The rectifier. This we will do with a diode. We put just a diode in and a load resistance. And at that point, as a diode, we can use a 1 and 41, 48. Something like that. The load resistance might be 10K. And if we are looking at the signal at that point here, we are setting up the circuit on the breadboard. We put in the components and connect the oscilloscope. How many of you have used an oscilloscope? Not very much, but we will do that. And at the display of the oscilloscope, what will we see there? We will see only the positive half of the signal. That means the positive signal share will be there. the negative signal will be stopped by the diode. It will be gone. So that means we have the next positive peak, 0, the next positive peak, 0. That's what we will see here. And since we will sample our sensor signal, this is not a very good idea to sample this signal, because sampling is done on a regular scale. It means we take some samples out of the signal. So we have a lot of samples that are 0. But this is an artifact since our real signal will be negative here. That means we do some averaging on that signal. And the averaging we do with a low pass filter. It's an RC filter for averaging. So we take here maybe 10 microfarads, and here we take our another 10K resistor, and after that we should see a signal looking like that. And maybe I also bring a microphone with me to the lab, and if the circuit works well with the sinusoidal signal, then we can try it with the microphone. That you see what this averaging circle will get you.
What is the next? The copper one? The same thing? Yeah, the same thing. Yeah.
This is the same resistor like here.
Oh.
But it must not be the same, but... And then the sampling will take samples out of this signal. And this will be more or less the maximum value of our input signal. But we won't do the sampling, because this is too complicated. We will do only the first step in this sensor chain, the signal processing. We will have our rectification and then the averaging, or the peak detection. Because it's not quite an averaging filter, it should be more or less a peak detection. And here are parallel to see, we will set a very high resistor, maybe 10 mega ohms, to decharge the capacitor. Because otherwise the capacitor will be decharged around here. So we don't need that one. So the first thing will be to manage the generator to set up the correct output parameters. The frequency should be 1000 Hertz. And then have a look at this output frequency at the oscilloscope. You will see it there on the screen. Hopefully the same sinusoidal wave. I will explain to you the cables, how you can link the generator and the oscilloscope. And then we will set up the amplitude, frequency, and you can see, and you can scale down here to 1 second, and then you will see that there are 1000 excursions per second. And this 1000 excursion per second means that we have a signal with a frequency of 1000 Hertz. And when we have set up this, then we will set up the circuit on the breadboard. For the breadboards, there are two columns of holes. On the outside of the breadboard, there are some additional rows. The inner columns there are 5 holes where you can put your components, and they are all connected in that manner. So all these 5 holes are connected together, and the lines are all connected in that way. Yeah. There in the middle there is a separation, but has no electrical properties.
Excuse me, this low pass has the average,
This low pass normally gets the average. Yeah?
and about it chooses the high peak. Yeah.
For our case, since we have this diode here, it's more or less that we got the peak values. Because there is much faster charging of the capacitor than decharging due to this diode here. Huh? Any other questions? So then we will see in the lab, it's in the other building, on the upper side, the 6th floor, room 26.
Thank you.
You see